Okay guys, today's lesson, let's look at today's lesson. It's on parametrization. So we spent a few days on parametrics and we learned how to eliminate the parameter. Remember that we figured out techniques, we used substitution and other techniques to eliminate the parameter. What we're actually doing today is we're going to be going the other way. Instead of eliminating a parameter, we're going to be introducing a parameter. We're going to change a rectangular equation into a parametric equation. So we're going the other way. Now that we hopefully are fairly comfortable eliminating the parameter, we're going to introduce a parameter. So there's a couple of main things that we would parametrize. One of them is a line. So let's look at the system or the technique that we use for making parametric equations out of a line, a rectangular line. We basically need 2 points on the line, point A and B. Sometimes we're given those points, sometimes we're not. So here's our steps. The first thing that we would do is we would find the vector from A to B. Now, do you have to find the vector from A to B? Could you find it from B to A? Yes, you can. But what I would like to do is for us just to be standardized, so we do the same thing. If you create your parametric equation in a different way, then it's going to look different than everyone else's parametric equation. It'll still generate the line, but it's going to look different. So let's just kind of standardize it. And so the first point, whatever the first point is, that's what I want you to have as your initial point of the vector. And the second point would be your terminal point of the vector. And so we know how to write a vector from 2 points. We've done several weeks ago. So then we would add a scalar multiple of the vector to point A. That's the second thing that we would do. And basically what I ask is that you add the first point A. And we'll do an example of it so that you see, so that our equations look similar instead of completely different. So that's how we would parametrize a line. Well, what about a line segment? What would we do? So with a line segment, there has to be a beginning and ending, right? There's not a continue forever. And if you parametrize the line with these steps that I've given you, do it exactly this way, then to restrict it to a line segment, it's always going to be from 0 to 1. And I'll show you why that is when we do one. If you choose to parametrize a line a different way, then it's not going to necessarily be 0 to 1 and be something else. So that's another important reason why you should just keep it like I'm showing you. Don't mix it up. Can you mix it up? Yes, but let's not. Let's just keep it the way that I'm demonstrating to you. The other thing that we'll be looking at is parametrizing a circle or other kinds of figures like an ellipse or something. So I need to remind us, well, we need to be reminded, I'm sure you probably remember, the standard equation for a circle. The h being our x coordinate of the center and the k being our y coordinate of the center. Remember, so x squared plus y squared equals r squared, that's centered at the origin. We will be working with different kinds of circles, not necessarily centered at the origin. And r is still, our radius. And we will be using sine squared plus cosine squared as 1 with this. Remember how we used it when we took the parameter out? We used the sine squared plus cosine squared and we turned it into a 1. We're going to be going backwards today. We're going to turn the 1 into sine squared plus cosine squared. We're just going to reverse our work from previously to change the circle up. All right, so let's jump into some examples. The first example is finding the parametrization for the curve. And I know a line isn't curved, but we typically call all those things curves. Like in the rectangular plane, we call them curves. So we want a line segment with endpoints. We're going to do it the same way that we would parametrize a line. We're just going to add this restriction to it. So let's walk through those steps. So the first step, we would find the vector from A to B. So this A to B, we're going to find that vector. So vector AB, and we know how to do that, right? End minus beginning. So we would do 3 minus a minus 2 and 4 minus 6. And so our vector AB is going to be, 5, negative 2. That's our vector. So we just did step 1. We found the vector from A to B. Step 2 is we're going to add a scalar multiple of the vector to point A. Basically what that's saying is we need a point on the line. We would find a point on the line and we would add it to the vector. And what I'm encouraging you to do is to make the point that you add a. Make it the first point. So we're going to put it in a vector equation. You might recognize this from the other day. Remember how it was xy equals, and then it had this point. We're going to use negative 2, 6. We're going to use point A plus t times the vector 5, negative 2. Remember that? How that vector equation of a line? And we took this and we turned it into parametrics. Remember how we matched the x equals negative 2 plus 5t? Remember that a few days ago? That's so I'm going to a vector equation. I'm going to turn it into a parametric. So I'm going to match up the x equals negative 2 plus, I'm going to distribute the t. So my parametric equation is going to be x equals negative 2 plus 5t and y equals 6 minus 2t. Do you remember that from the other day, how we wrote that? And now I'm going to add the restriction. I'm going to add the restriction this because it's a line segment. So 0 less than equal t less than equal to 1. So let's investigate why does that work. I need you to understand why it works. So I want the line segment to start at negative 2, 6 and end at 3, 4. I mean, that's what I want. So what happens if I put a 0 in here for time? If I put a 0 in here for time, what point do I have? Negative 2, 6. That's what I want, right? If I put a 1 in for t, what point do I have? I have that one, right? 3, 4. So if you create the parametric equations like I'm teaching you, this is always going to be your restriction, always for a line segment. If you choose to do them a different way, then that's not going to be the case. You would have to change this. So I encourage you to just create them the way that I'm showing you. Okay, because that's always going to work. The 0 is going to eliminate that, and you're going to get the first point because we started out our equation with the first point. And then the 1 is going to generate the second point. Okay? And that's how we parametrize a line segment. On the next one, we want to parametrize the vertical line x equals 2. We're not given points. So here's what I encourage us to do. Let's look at this. So we have a line. Okay, so we're looking at this line. So here's the points that I encourage you to choose. Do you have to choose these points? No, but I encourage us to, to be standardized. So I would encourage you to choose the point where the line crosses the x-axis, that point. So that point would be 2, 0. And then I would encourage you to choose the point that's 1 unit above that, this 1 unit above that on the x-axis. So that's going to be 2, 1. This is just going to simplify our work if you choose those 2 points. Again, you don't have to. So now we're going to go through the same procedure. This is going to be our point A, and this is our point B. We're going to write our vector. So vector AB is going to be 2 minus 2, right? And then 1 minus 0. Or our vector is going to be 0, 1. That's basically a vector in simplest form, 0, 1. Could we write another vector that was headed that same direction? Sure. Sure we could, but it wouldn't be in simplest form. Think about what that vector's doing. It starts at the origin, right? And it doesn't go, basically it doesn't go left or right, it goes up, right? It goes up. So I could write 0, 5 and it would still go up, right? But 0, 1 is in simplest form, so let's do that. So now let's do our formula right here. So we have xy equals, I'm going to choose my first point, plus t times my vector. That's how we write it. We go to the vector form first. Now what I'm going to do is I'm going to take that vector form and I'm going to create the parametric equations out of it. You know how I match the first spaces for the x and the second spots for the y. So x is going to be 2 plus 0 times t. That t is going to go away. We'll simplify it in just a moment. And y is going to equal 0 plus t. Now you can certainly leave it like that. I'm okay if you leave the 0 in there because that's kind of like, it makes sense. But why don't we just go ahead and simplify it? Let's kind of clean it up a bit. So we would have x equals 2 and y equals t. That would be our set of parametric equations that would generate the vertical line x equals 2. Okay, how are we with that? Okay? Mm-hmm. Yes, I encourage you to. Do you have to choose the first point? No, but I encourage you to choose the first point. That just makes our lives simpler. Yeah, so just choose the first point to put in your vector equation, whatever the first point is.
Any 2 points along the line?
You can, sure, you can. Mm-hmm. Yes.
What did you say the first one you should choose when it goes to the y-axis and goes to the second one?
On this one, the first, when it goes through the x-axis, the next one is the one above, 1 unit above. Just makes it easier. Do you have, no, you don't have to. You can choose any point you want, but just to make it easier for us. Mm-hmm.
Is the restriction only on line segments?
Well, the restriction would be on line segments or anything that you want to stop. Okay, on a particular line, we would want to let that go on forever in both directions, right? So we wouldn't want to restrict a line, but we would want to restrict something that's stopped. Let's say we wanted to create a semicircle. We would want it to stop, right? So we would need a restriction on it. In fact, that's going to take us to our next problem. So let's go to problem number 2, where we're going to work on parametrizing a circle. Okay. So first, what we want to do is let's write the equation of the circle in Cartesian form. And so this would be centered at 0, 0, right at the origin. We actually want an equation where we're translated 3 to the right and 5 up. So our h and our k are going to be different, aren't they? So instead, our equation would be x, let's see, we're translated 3 to the right. So x minus 3 squared plus and 5 up. Y minus 5 squared equals, and our radius is the same. So that's the equation that we're going to parametrize. Now we're going to go backwards from how we parametrized before. Remember, or when we eliminated the parameter, remember how this was a 1 because it was sine squared plus cosine squared, and we made it a 1? We're going to do that. We're going to go backwards, right? We're going to make this a 1, I would need to divide everything by 36. Right, so let's do that. We're going to go backwards. We're going to divide everything by 36. So I have x minus 3 squared over 36 plus y minus 5 squared over 36 equals 1. Okay, do you remember what we did before that? Before it became a 1, we had sine squared and cosine squared here, didn't we? So let's replace the 1 with sine squared and cosine squared. So I have x minus 3 squared over 36 plus y minus 5 squared over 36 equals cosine squared t plus sine squared t. Now, the step before this is where we added 2 equations together. Remember that? We added 2 equations together. Now I'm going to break them apart. I'm going to break them apart. And it matters what I match. If I match the x and the cosine and the y and the sine, that's normal, right? That's normal. What is a normal rotation? Counterclockwise. Normal is counterclockwise. So if you're asked to have your circle rotate counterclockwise, you have to do the x with the cosine and the y with the sine. What happens if we want to go clockwise? What do you think you would do? You'd switch them, match them differently, right? I would match the x with the sine and the y with the cosine. That's going to be significant because you're going to be asked to make it rotate one way or the other. Okay? In this particular problem, they're leaving it up to us, so we can just go crazy, right? Just pick whatever we want. But you're typically going to be told which way to make it rotate. So I'm just going to go with the norm. I'm going to match the x with the cosine just because, I like counterclockwise. So let's do that. So I'm breaking the equation up. I'm matching the first piece with the cosine and the second piece with the sine. Do you remember going backwards? We're going backwards now. What would we have done to get to this? We would have squared both sides, right? So now we're going to need to square root both sides, right? We're going backwards again from where we were. So this turns into x minus 3 over 6 equals cosine. And this turns into y minus 5 over 6 equals sine. And then what do you think we do from here? Yeah, we just move things around. We're going to solve for x, we're going to solve for y. So I would multiply both sides by 6, right? And then I add the 3, so I get x equals 3 plus 6 cosine t. And then over here, I'd multiply both sides by 6. And so I get y equals 5 plus 6 sine t. Now let's talk about the rotations of this guy. If I don't put a restriction, how long is the circle going to rotate? Forever. Think about that. Poor little thing on a loop, just circle over and over. It's like, oh my gosh, I've already been by 0 before. I got to go by it again, you know, all the way around. So why don't we help it out and restrict it? What would give us a complete circle? 0 to 2 pi. Why don't we just lend it a hand, right? Let's just restrict it from 0 to 2 pi. So that we just have one rotation of the circle. What if we wanted a semicircle? What would we do? We'd do 0 to pi, wouldn't we? Wouldn't that give us a semicircle? What if we wanted a quarter circle? Okay, so we got the idea, right? 0. So that would restrict it to give us exactly what we wanted. Okay, how's that? All right, on the next problem, we are actually going to introduce a parameter, but we are told what the parameter is on number 3. So we're told that we're going to introduce a parameter t equals x, and we're going to introduce the parameter, this different one. So let's do the introducing the parameters first, and then we'll deal with the graphing and speed and orientation. We'll deal with that in a moment. But let's first parametrize this. This is the curve that we're parametrizing, and I think we all recognize that's just a parabola, right? It's been shifted down 4. So we're going to parametrize this curve. The first way we're going to do it is by using the definition that t would be x. So I'm going to replace that x with a t, and that's the y part of my parametric equation, and the x part, I mean, it's already given to us. Right, so that's my set of parametric equations for this parameter, part t, x equals t. For the second one, I have a little bit more work to do. This is a bit more complex. I need to solve it for x, right, because I've got to get rid of this x and put a t in it. That's what we did here. That's what we're going to do on the second one. So I need to solve this for x. So I have t minus 1 is 4x, or 1/4 t minus 1 equals x. Okay, so that's what I'm going to use to substitute in here. So this is going to be a little bit messier. So I have y equals, and for the x I'm going to place this in it. So I have 1/4 t minus 1 squared minus 4. Wow, doesn't that look super fun? Look at that. Whew, we get to square and FOIL and combine like terms, just algebra craziness right there. So let's clean it up. So I square 1/4, I get 1/16. I square t minus 1, and I get t squared minus 2t plus 1 minus 4. And you're thinking, oh, that looks great. What is it going to become, right? What's going to happen? I would distribute the 1/16, combine like terms. After all is said and done, I have this fantastic looking equation, y equals 1/16 t squared minus 1/8 t minus 63/16. Wow, that's fantastic, okay? And that's my x component of this one. Now my y, that's my y component. My x was right down here, which is 1/4 t minus 1. So this is the set of parametric equations for the second one. Okay. So now that we have that done, we introduced the parameter that they required us to. We're good. We've parametrized that this in 2 different ways. Our graph is going to look exactly the same, right? It's still going to look like y equals x squared minus 4. So what I encourage you to do in a scenario like this is we're going to pick the points that we want to find out what's going on. What we're trying to do is we want to look at the speed and orientation. In other words, which way is it going? Is it going right to left or left to right? And how fast is it going to get there? We don't need to actually calculate a speed. We just need to show it on our graph. So what I'm going to do is I'm going to pick the easiest points I can think of that are possible. Like I'm going to pick that point, right? This is translated down 4. I'm going to pick that point. Also, I would like to pick the points where it crosses the x-axis, which would be what? Plus minus 2? So I'm going to pick these points right here. And I'm just going to throw in one other point for fun. Let's throw in plus minus 3. So that would put us, if I put a 3 here, that would give us, what, 5? So that would be like up 5. So here and here. Okay. So I know my parabola is going to look like this. Okay, I know that. That's fine. What I need to determine is what are the t-values at each of these points and which way am I going? Okay, so how do I do that? Well, I'm going to go back to my, this is A, I'm going to go back to this equation. X is t. They're the same. So if my x value here is a negative 3, what's my t value? A negative 3. T equals negative 3 right there. If my x value here is a negative 2, what's my t value? Negative 2, because x is t. They're the same. So t equals negative 2. If my x value here is 0, what's my t value? 0. T would be 0. If my x value here is 2, what's my t value? We're getting the hang of it? Right, t would be 2, and t would be 3. Now, it's going this way, my orientation, right? It's going this way. That's my orientation, got my orientation. Let's talk about speed. What I encourage you to do is just look at the time difference here between the beginning and ending of the segment that you drew. Okay, that we're gonna call it seconds. 6 seconds. They don't tell us the unit of time, so we get to make it up. Okay, 6 seconds. It sounds way better than 6 units of time. Right, I mean, if you want to do 6 years, go for it. Write 6 years there, but I'm just doing seconds. So on the second one, we have to we've parametrized it. Now we need to graph it. I'm going to use the exact same points, the exact same graph. Okay, no differences, because it is the same graph. I mean, the graph itself is the same. Okay, so I just don't know which way it's going, and I don't know what the time lapse is. So I'm going to make this a little easier to calculate with. I like fractions, okay, but it's really hard to calculate with fractions, so I'm going to multiply both sides by 4, and this is going to be 4x equals t minus 1. Okay, that's going to help us calculate. What I need to do is put my x value in here so I can see what my t value is. If my x value is a negative 3, 4 times negative 3 is negative 12. Negative 12 plus 1 is negative 11. This is a t value of negative 11. If I put a t value of negative 2 in here, an x value of negative 2, 4 times negative 2 is negative 8. Negative 8 plus 1, negative 7. Check my arithmetic, it's not the best. We okay? If I put an x value of 0, this is an x value of 0 in here, my t is going to be 1. Which way is this going? It's going the same way, isn't it? It's going this way, just like the other one. Does it have to go that way? No, it depends on what parameter they give us. If I put a x value in of 2, what does that give me? A 9. And 3 would give me a 13. How long did this one take to go the same distance? How long did that take? From negative 11 to 13. Isn't that 24? 24 seconds? So this one traveled much slower than this one. That's all they want to know is speed. We don't have to actually calculate the actual speed. Okay? All right. Then our very last problem. Are we good with that? It may take time to sink in. I know it's kind of like, wow. All right, the very last problem, I went ahead and did a t-chart for it so that it would help us move a little faster through the problem. I just got the t-chart out of the information from here, out of the x and the y, that's all. We're just going to graph it because really the purpose of this problem isn't the graphing. We know how to graph parametrics. The purpose of this problem is to answer this question. Find the values of the parameter t that produce the graph in each of the 4 quadrants. That's our purpose for this. So let's graph it first and then investigate what that's going to be. So I'm going to do my graph in like little half points because of this. So all these half points. So see. Okay. So that's how I'm going to set my scale, basically go by halves. All right, so let's start with the first point here. When time is -3, we would have an x value of -1 and a y value of -4.5, so that would put us right down here. And then when time is -2, we would have an x value of 0 and a y value of -3.5. So we are going this way. Then when time is -1, we have an x value of 1 and a y value of -2.5. Continuing our travel, x value of 2, y value of -1.5. So about right there. Then when time is 1, our y value is 1 and we're at -0.5. So like there. Let's see, so now we're at 0.5. And then at -1, 1.5. And then at -2, 2.5. Okay, and that gives us our parametric graph. So now let's figure out what in the world they're asking. Find the values of t that produce find the values of parameter t that produce the graph in each of the 4 quadrants. So what we've got to try to figure out is at what time were we in quadrant 3? At what time were we in quadrant 4? That's what we're looking for. So I'm going to set up the quadrants. So we're looking for the time we were in each quadrant. Okay. Now sometimes this is going to be easy to determine, sometimes not so easy. So when we cross out the y-axis, we cross into different quadrants, right? When x is 0. So let's just take our, do some algebra here. Let's set x equal to 0. When x is 0, I would have 0 equals 2 minus absolute value t. So absolute value of t is 2, so t is plus or minus 2. And we actually could have gotten that off of the chart. When x is 0, t is plus or minus 2. Okay, so that's going to be important for us. When we cross the y-axis, it's going to be either at 2 or -2, depending on where we are. What about when we cross the x-axis? What about when y is 0? Do we have the point where y is 0? No, we really do have to calculate that point. So if I want to know when y is 0, I would go here, right, and I'd put a 0 for y. So 0 equals t minus 1.5. So t is going to be 1.5 when we cross the x-axis. The time, we're looking for times. Okay, so I think we have all the pieces of the puzzle. Let's start at the beginning. So we're in quadrant 3 right here. What time did we start in quadrant 3? At -3, right? So -3. Are we in quadrant 3 at -3? We're inside the quadrant, okay? So less than equal to t. So when do we leave the quadrant? We leave the quadrant when we cross the y-axis. When x is 0. When is that? We leave it at -2. We're not in the quadrant at -2. We're on the quadrantal, so we can't put an extra equal sign there. Okay, because we're on the quadrantal. That's not considered in the quadrant. Okay, so that's my quadrant 3. Okay. Now let's move to quadrant 4. Let's just go in order of our graph. So quadrant 4, when do we first step into quadrant 4? What is our time when we first step into quadrant 4? -2, right? So -2, and I can't say I'm in quadrant 4. I have to say less than, t less than. What time do we leave? Right here, what time do we leave quadrant 4? We calculated that already, didn't we? 1.5. We leave it at 1.5. At 1.5, I'm on the quadrantal. I can't put an extra equal sign. What quadrant are we going into now? Quadrant 1. So I'm going to start in quadrant 1 at 1.5. Right? When do I leave quadrant 1? When my x value is 0, I leave it at 2. Okay? And then quadrant 2, I begin quadrant 2 at time 2, and then when do I end? At 4. Now, am I inside quadrant 2 at time 4? Yes, so I put the equal there. So the equals would just go, I mean, typically at the beginning, at the end of this, right, when we're actually in the quadrant, unless we happen to start on a quadrantal. And this is the information that they're looking for. Okay? That's the information they're looking for. All right, how are we doing?